So when I captured my voice into MATLAB and I took the Fourier transform of that, I wasn't really taking a continuous Fourier transform that we just defined. Instead, I did not have this continuous signal y of t. I didn't have an analog signal at my disposal. MATLAB had to sample my voice, it even quantized it, right? And instead what I had was a discrete signal. So not even taking into account the fact that there was some ADC and some quantization, right? I instead have to think about taking the Fourier transform of a sampled signal. And so there are all sorts of interesting consequences to that. But let's start with looking at the definitions, right? My continuous Fourier transform that we've already defined, I have a continuous function of frequency, I have a continuous function of time. Right? And so my coefficients are a continuous function of frequency, and to calculate those coefficients, I'm integrating my continuous function of time multiplied by a complex exponential at the frequency that I'm interested in looking at the coefficient for. For my discrete Fourier transform, I'm also calculating complex coefficients to describe amplitude and phase at different frequencies, but I'm not looking at continuous frequencies anymore. Right? In this case, the k here is referring to my kth frequency bin. So instead of this continuous function of frequency, I'm going to divide my possible frequencies up into bins. So think of it as a histogram, effectively. And so to calculate that, I'm summing over all of my samples, right? My little y of n. I can also think of this as a y, n in square brackets, depending on how you want to represent sampled signals. And similar to the continuous time Fourier transform, I am now multiplying by a complex exponential, e to the minus j, 2 pi k, which is referring to that kind of frequency of interest, little n, which is my current sample I'm looking at, so kind of like the t up here, divided by big N. One way to think about this, if it's hard for you to go back and forth from continuous to discrete time, is this k over n, so this kth frequency bin, divided by the total number of samples in my signal is approximately equivalent to the frequency that I'm looking at, and my n, little n, is approximately equivalent to my time in the continuous function. So let's unpack what's actually going on here a little bit. So this is my definition for the discrete Fourier transform. I'm taking all of my time samples, little y of n, multiplying them by this complex exponential. And I'm going to take this whole term right here to simplify my life a little bit and just write that as little bn, so I don't have to keep writing out this giant fraction. And if I write out my y of k, if I kind of expand this sum to get some view of what I'm looking at whatever my first sample is, the amplitude of that first sample, times e to the minus j b naught, right? And in this case, I also know that that b naught is going to be 0 because I have an n equals 0 term here, plus y1 e to the minus j b1 plus da-da-da-da, all the way up to yn e to the minus j bn minus 1. So you can see I'm taking each of my samples, so the actual numerical value of that sample, and multiplying it by a complex exponential that's tied both to the sample number and the frequency bin that I'm interested in looking at. Now we can use Euler's formula to break this up into something that we can more easily calculate. So e to the jx is going to be cosine of x plus j sine of x. And so if I rewrite my y of k with that in mind, I'll write my first sample times the cosine at my frequency, so minus b naught in this case, plus j sine times that frequency minus b naught. And I can keep doing that for all of my samples. So ultimately, when I'm writing my y of k, I'm going to have a combination of real signals here. So all of these cosine minus b naught terms are going to be my real signals. So I can write those as some a of k again, plus some combination of the imaginary terms, so all the sine terms here as well. So it'll be plus a j bk. So as I mentioned previously, I could have done this with the continuous time Fourier transform as well. But now I have, for each of these frequency bins, a coefficient, a complex coefficient, and it has a real term, in this case I've designated it by A, and an imaginary term designated by B. So I can think of that complex coefficient as a vector in the complex plane. So the complex plane is typically written as the x-axis refers to the real part of the term, the y-axis refers to the imaginary part. So if I plotted out my complex coefficient that I've defined here, along the real axis would be AK, and the imaginary axis would be BK. So one thing that you can see from this is that this term right here, this complex coefficient, has a magnitude and it has an angle or phase. And I can calculate that magnitude and phase. So if I'm looking at the magnitude of YK, I'm looking at the square root of the square of the real part plus the square of the imaginary part. And similarly, I can calculate the phase of my complex coefficient. So sometimes I write it as phi of y of k, sometimes I might write it as the angle of y of k. Regardless, that's equal to the inverse tangent of the imaginary part of my coefficient divided by the real part of the coefficient. And that's also representing a complex sinusoid. So in this case, it's always going to represent a cosine function with an amplitude and phase. So here's my basic cosine function, and I can give this here the amplitude that's going to be my magnitude of y of k. And I can think of this phase basically as a shift in my sinusoid. And that'll be based on the angle divided by the frequency that I'm looking at.